All right, welcome to the video on using least common multiple and greatest common factor in real-world situations. So we started on page 51 because we needed a little bit of review on prime factorization. Remember, prime factorization is when we split numbers into factors other than 1, because 1 is not a prime number, so we don't want to use it. So we're breaking numbers like 21 into 7 times 3, and then asking ourselves, can I go any further? And I can't, because 7's prime and 3's prime. But we want to list it as 3 times 7 because you usually go in order from least to greatest. Okay, and another example is 30. Break 30 into 3 times 10, and then bring 3 down because it's prime, and then we split 10 into 5 times 2. But rearrange it so it's 2 times 3 times 5. And then last, we did 42. 42 could be broken in several ways. We chose 21 times 2, and 21 is broken into 7 times 3 times 2. And again, we'd probably want to rewrite that as 2 times 3 times 7. Okay, so that's prime factorization. And we looked at the next page. And I encourage you guys to read through this, and I had you all figure out ways to go about this. And we got different ideas. But we went with this listing all the factors. So we listed all the factors, or pairs of factors, I guess, of 40, 72, and 24. And the idea we got to was the biggest number that they could all be broken down into is 8. All right? So entered a new way of looking at GCF. It's the biggest number that goes into each number involved. All right? Nothing bigger than 8 can go into 40, 72, and 24. But we don't want GCF to be our answer. Our answer is going to be answering this question. What's the greatest number of packages? Well, 8 packages would be our answer. And then to describe the collection, the used package will have 5 spacers, 9 round beads, and 3 rectangular beads. And how did we get that? Well, we know that we're going to break all these pieces into 8 different packages. So in other words, if I divide 40 into 8 different packages, how much will be in each? So it's really basically 40 divided by 8, which would be 5. That's how I know it's 5 spacers. And then so on and so forth. 72 divided by 8 would be 9. 24 divided by 8 would be 3. All right? But we spent a lot of time on this, but this is really kind of what it boils down to, is how can you use GCF and LCM in real-world situations? And I told you one of the biggest tricks, well, we'll get to that in just a little bit. Sorry, come back to that. So enter this new idea. What's the biggest number that goes into both? That's a new way of looking at greatest common factor. So 36 and 48. What's the biggest number that goes into 36 and 48? 2 works, right? Because you can divide 36 by 2, and you can divide 48 by 2. 4 would also work. 4 goes into 36 and 48. But that's not the biggest number that goes into both. 12 is the biggest number that divides into 36 evenly. There's the key there. It has to be evenly, whole numbers, and 12 goes into 48. Okay? Then they wanted us to rewrite each numeric expression using the distributive property. So what we did here is we pulled this 12 out. Okay? It's kind of like extractions. Okay? I'm extracting a 12 out of 36. So what's left over? Well, 36 divided by 12 is 3. And if I'm extracting a 12 out of 48, what's left over would be a 4. All right? So that's kind of how we rewrite an expression using the distributive property. What we call this later on in math is factoring out. And you'll do a lot of this in algebra and beyond. But for now, we're just kind of introducing this idea. Okay? Like I was saying, one of the biggest tricks is to know, am I working with GCF or LCM? Because you probably guessed, it's one of the two. Right? So we looked at this situation. All right? And if you read this, the first machine makes a part every 12 seconds, and the second machine makes a part every 45 seconds. So what I would recommend you doing is writing out, okay, so it's going to make a part at 12 seconds, and then it's going to make a part after 24 seconds, and then a part at 36 seconds. What am I doing here? I'm just counting by 12s, right? Or in other words, the multiples of 12s. Then I would do that with 45. Okay, the second machine makes a part at 45 seconds, and then again at 90 seconds, and then go from there. And do that until you see an overlap. Okay, so at what time will they make apart at the same time? All right, that's kind of what's being asked here, is how often does Rana test the parts? Because it's when they overlap. All right, and notice, be very careful here, it wants your answer in minutes, not seconds. So you have to do a little bit of converting. You'll probably find an answer in seconds. Don't forget to convert it to minutes. All right, so that's LCM, because we're looking at time. All right, we're projecting out, which means we're probably looking ahead at multiples. So time is kind of a dead giveaway that it's LCM. Maybe not always, but more times than not. And then this next one, as you probably would guess, is a GCF problem. But why? Well, this is a key word right here. He's dividing these kids into groups. Anytime we're dividing or splitting, it's probably GCF. So what you're going to need to do, well, it says, what's the greatest? Oh, sorry. I got off. So how many different ways can he divide his groups? Okay, so you're going to have to look through and figure out the different possibilities. All right, and then what's the greatest number of teams Mr. Ellis can make so that each team has the same number of 9-year-olds and the same number of 10-year-olds? Okay, so really, I think you're going to make a list of common factors, right? So you're looking at different ways you could break them up, different numbers of teams, so that everybody has the same number of 9-year-olds and same number of 10-year-olds. And then B is just what's the biggest number of teams? Okay, it sounds like GCF to me. All right, and then C you do not need to do. All right, and you can look at it, but you will not be graded on it. All right, so hopefully that helps somewhat. Feel free to watch this video as many times as needed to help you understand these concepts. Thank you. Bye.